So first, let me introduce Laixi. It's my great pleasure to have Laixi here to give us a talk. Laixi was my intern like 5 years ago, 2020, in the summer. Because it's COVID, so she worked remotely. So I haven't got a chance to see her since that. Later in the ICASP, I met her. She received her PhD from CMU in 2023, and her advisor is Yue Jie. Many of you may know her advisor, also a former MERL intern. And after her PhD work, Laixi did a postdoc research at Caltech for about 2 years. So last summer, she joined Johns Hopkins as an assistant professor. And she has done a lot of interesting work on reinforcement learning and inverse problems. And also she received a lot of awards, including 5 Rising Star Awards in different areas, and also dissertation award, yeah, and some others. So yeah, welcome back, Laixi. So to your talk.
Thanks, Hong, for the very kind introduction. Yeah, good afternoon, everyone. It's truly an honor to come back and share with all of you my some of my recent works. So this talk will focus on leveraging mostly. So I have done works mainly in inverse problem for signal processing, including the project I worked with Hong when I was an intern here about image staging for some mechanical engineering applications. I also done a lot of works on sequential decision making, especially within the reinforcement learning frameworks. So this talk will have 2 parts. The first part will be about reinforcement learning, and the second part will be about multi-agent systems, drawing some inspiration from behavior economics to for some computation tractability. Okay, so first I want to express my gratitude to all my wonderful collaborators who make this interesting finding possible. So this is just a non-exhaustive list. So as Hong mentioned, I was an intern during my PhD in MERL, and my PhD advisor was also an intern. So that's very interesting truth thing for me to be very connected here. So I'm very excited and also look forward to exploring mutual interests and potential collaborations in the future. So I will just start. I will give a very brief introduction for the topic, general topic. So humans make decisions every hour, every day. And recently, AI capable of making decisions has advanced rapidly, impacting human society, manufacturing, and science. For example, Tesla's self-driving cars automatically navigate to save passengers' time, and robots can help manufacturing efficiency. And for biology and chemistry, AlphaFold from Google DeepMind can predict protein structures, may helping to replace classical, costly, and time-consuming experimental process. And in healthcare, AI is potential to improve clinical treatment, and there's also a good direction of surgery robots that is very promising in the future. So generally, a decision-making AI pipeline involves 2 phases: training and deployment. So first, during training, we will first define a goal for an AI, such as let a robot to pick up bottles or developing a clinical AI to recommend optimal treatments. Then when the training process begins, we will first need to get some data, which is the foundation of AI. And then a general learning framework is applied to extract information from those data and ultimately produce a solution. For example, in robotics, we can collect demonstration using remote operations from human experts as data, and then let the robot to learn by solving optimization problems to mimic the expert. And once the training is done, it will be deployed in the real world, where the task it handles might match the original goal or might deviate due to uncertainty or variability of the world. So this is a very basic overview of how a decision-making AI is built and utilized. So just two phases, training and then use it. So is such AI ready to be used in real world? Will significant progress has been made. In many cases, transitioning AI prototypes to real-world applications can still be frustrating, hindered by several bottlenecks. Oh, sorry, I forgot to mention, if you have any question, don't hesitate to just interrupt me. Yeah. So I will first introduce the 3 challenges that will be tackled in this talk. One is the short, which is also very fundamental challenges in these data science or AI world. So one is the shortage of training data. So AI could require massive training data, like trillions of points in various fields, like pre-training GPT-4. But data is always limited, and many organizations are running out of usable data due to the quality issues, privacy, or high costs. And in many high-stakes fields like robotics or healthcare, collecting data could be more challenging due to some hardware constraints and also regulatory compliance. And another big challenge is compute. And the cost of compute isn't just about money, it's also about time and energy. So for example, NVIDIA has made a fortune from AI with its data center revenue grows extremely fast. If we only use 1v100 GPU, training GPT-3 could take 288 years. So that's why people use so many GPUs parallelly currently. And another thing is like data center consume energy at rates comparable to some entire countries like Sweden or Germany, posing significant challenges to energies like power grid and also global sustainability. And even with extensive training using so many data and compute, AI can still struggle in uncertainty during deployment. Some unexpected scenarios can immobilize self-driving cars to cause traffic jam. And in healthcare, some shifts in data distribution caused by variations in scanner models or technician settings may cause AI failure in radiology. So far we have introduced 3, let's say, bottlenecks or challenges that can hinder decision-making AI from working in practice, posing an urgent need to design better algorithms that can handle this learning efficiency and robustness. So for learning efficiency, what is desired that we want to design training algorithms that can minimize the need of data, both data and compute during training. That's what we call like data efficiency and computation efficiency, respectively, all belonging to learning efficiency. And at the same time, we seek robust AI, providing reliable performance even when dealing with unseen inputs or circumstances. So with these 2 goals in mind, can we design? So it motivates us to ask whether we can design a framework that achieves both learning efficiently during training and also being robust during practice, during like deployment. So actually, it's very challenging to achieve both. Current frameworks often bring in robustness at the cost of learning efficiency. Because you can imagine like adding robustness as an additional goal can conflict with the goal of learning efficiency, introduce additional burden that potentially slow the learning process. So specifically, there exists to be more specific about what I have seen. So there exists two main directions that people usually use to bring in robustness. The first way is to improve the dataset. Training on larger and more diverse dataset could help AI generalize to unseen circumstances. For example, if we train a robot on more diverse manufacturing scenarios, it could prepare it to handle unseen but similar tasks in the future. However, this often sacrifices data efficiency, as covering the variability could require a manageably large data set. And another, like the second way, is to focus on improving the data processing framework, which often comes with higher computation costs. For example, designing new optimization objectives by adding constraints to avoid risky decisions, or using some ensemble learning like boosting bagging, or more advanced or some framework like meta learning and transfer learning domain adaptation. Those ways either need more complex algorithm to solve, or they need to train on multiple model, or train on like extending the learning process in more environments. So both directions will trying to bring robustness at the cost of either data efficiency or computation efficiency, or sometimes both. So far, I hope I already convey the message that currently actually if we want to achieve the robustness, it's usually like we need to sacrifice some learning efficiency. So this leads us to consider, is this a necessary thing? So are robustness and learning efficiency truly conflicting goals? So in this talk, I will share some insights on how enhancing robustness in AI is not just a pressing need, but also an opportunity. So by understanding and designing effective optimization objectives, we can improve robustness without compromising learning efficiency, and sometimes even accelerate learning by leveraging the good implication of robustness. Yeah, I will present two cases that can highlight this insight. In the first part, we will focus on addressing the challenges of both data shortage and robustness together simultaneously, showing that it's possible to build robust AI for sequential decision making without needing additional training data. And in the second part, we will focus on multi-agent systems, address the challenge of compute costs and robustness together, demonstrating that by introducing robustness into agents' preference can improve computation tractability of learning games, something like non-robust counterparts often fail to ensure. Yeah, this is like the plan of this talk. So let's start from the first part about reinforcement learning. I think I may don't need to motivate reinforcement learning too much. It's actually a very powerful AI framework for sequential decision making, showing promise in aligning larger model and a lot of many other areas. So I will very briefly introduce what is reinforcement learning and the key notations to keep us on the same page. So RL is a framework where an agent learns by interacting with an unknown and black box environment. This interaction process is usually formulated as a Markov decision process, illustrated here for any time step t. So for a Markov decision process, it have 4 key components. The first 2 are the state and action space, which means where a state represents the current status of the agent and the environment, and action means the choices that the agent can act on to interact with the environment. So the entire joint space of state and action defines the agent's exploration space. And the other 2 things is unknown reward function and environment dynamics. People usually say it is transition probabilities, which is denoted as reward R and the transition P. Both these 2 things are unknown to the agent, forming the black box environment for it. So with this MDP in mind, the goal of in the RL task, the agent's goal is usually to find a policy, which is an action selection rule condition on each state that can maximize its long-term return, mathematically quantified as a value function shown here. Yeah. So if you view RL as an optimization problem, the objective is the value function, and the variable to be optimized is the agent's policy, pi, which is the pi condition on each state here. So the value function quantify the discounted sum of emitted reward that the agent receives during the process of interacting with the environment. And gamma is some discounted factors that determines how long the agent cares about the future. Yeah, that's a very brief introduction. Then if we focus on this kind of RL problems, and we train, we try to find the algorithm so that it can help us find the optimal policy. Will such a trained optimal, let's say, RL solution be ready to be deployed in real world? Actually, it will face the critical challenge, environmental uncertainty. So looking into this example, the task is control the arm to open the door, where the agent is a controller. So during training, the handle is positioned high, and the agent learns well. But during deployment, perhaps another door with a lower handle in the building. The standard RL may fail because it's overfit to training and didn't account for potential environmental shifts. Well, such shifts are very common. For example, for robotics and self-driving, agents can be trained in simulations, but face the well-known sim-to-real gap when deployed in the real world. And shifts can also happen due to disparities, like training on patients from one hospital but deploying in another, or from system noise or unexpected events. So there's a pressing need to enhance robustness in the face of such environmental shifts in reinforcement learning. So to address this, we follow a line of research called distributionally robust RL, which we refer to as robust RL later. If we transfer to solve this distributional robust RL, here's what we train. So we develop the robust RL solution and evaluate in both the training environment, the last one, and the shifted environment. So what is happening is that the robust RL solution performs well in both training and shifted environment. And even more surprising, it finds some general solution for the task, opening the door directly from the top with invariant of the height of handle. So robust RL can foster some smarter solutions that improves robustness and generalization, even without degrading performance in the original training environment sometimes. So here's how robust RL mathematically model environmental uncertainty. Recall that environment is formed by the reward function R and the transition kernel P. So for simplicity, we only illustrate the uncertainty modeling for transition kernel, which can be directly extended to the reward function. So we denote the transition kernel of the training environment as the nominal transition kernel PO. But during deployment, the transition kernel P of the environment may deviate from the nominal one PO. For example, the handle height changes or the distance between the arm and the door shifts. But we still assume that the deployment transition P lies within a neighborhood around the training one PO, denoted as the uncertainty set of U sigma PO. You can think it as a ball centered at PO and with radius sigma measured by some divergence function rho here. So various choice can be used as the divergence function rho. It's just to measure the divergence between any two transition kernel. So people usually can use some F divergence family, including total variation, chi-square, KL divergence, or using Wilson distance, or it can be also learned from data. So that's how the robust RL model this uncertainty set that the deployment may deviate from the training one. So with that in mind, we also want to specify a little bit about what is the data that both standard RL and robust RL use to train their agents. So here we refer to a very basic setting that they can only collect data from the unknown training environment PO, not the shifted one. So at each round, we can query any state action pair, and the generative model will allow us to do that and output what will be the next state as prime and the reward function, conditioned on the nominal transition kernel, which is actually the training environment. So after such independent n rounds, we will collect all the queries and their corresponding outputs here in the dataset D as our training dataset. So basically, the training dataset will consist of many independent transitions, like information. Okay, so now we are ready to give a very vivid illustration of what is the difference between standard RL and robust RL. So they will use the identical, both standard RL and robust RL will use the identical training dataset, D, as what we have introduced. But standard RL will assume that the training kernel remains the same during training and deployment. So the goal is to find the policy that can maximize the value function associated with this fixed PO. But in contrast, robust RL accounts for potential deviation of deployment P that is different from PO maybe, but still within a prescribed uncertainty set, UPO. So to enhance robustness, the robust RL agents aim to maximize the worst case performance when the deployment P is within this uncertainty set. So the only difference between standard RL and robust RL is that robust RL have an additional minimum operator in blue because it wants to optimize the worst case performance when the deployment transition P may deviate. So this operator will involve an additional inner optimization problem for a robust RL, making it more complicated to solve than standard RL. So, okay, that's the formulation of robust RL. So there will be only one more setting to see, like, so I want to introduce before we introduce the results. So we want to specify what the literature usually means by solving RL problems. So towards this, we denote the optimal output of standard RL and robust RL as V star and V star sigma, respectively. And so the goal, so what people usually say about solving RL problems is that they can find the almost optimal policy, which is called the epsilon optimal policy, which means that the performance gap between the optimal outcome and the outcome condition on or learned policy pi hat is smaller than some accuracy level epsilon. So this definition works for all RL problems. So now, as we see that robust RL is a more complex problem compared to standard RL due to its additional inner optimization problem, this raises an important question. So does solving robust RL need more data than standard RL? Or put simply, is that is there a trade-off between robustness and data efficiency? Do we need to pay a statistical premium to achieve additional robustness? So I'd like to share some insights that actually not. If we robust RL don't really necessarily need extra data cost than standard RL. To show the results, I make all of the theorem become figures, which is better for is I think easier to understand. So we begin by the data cost for solving standard RL, shown in the dashed blue line, which will be compared to robust RL shortly. So the x-axis shows the size of the uncertainty set, determined by the radius sigma. And y-axis shows the data cost need to solve a RL problem, namely finding an epsilon optimal policy. So standard RL can be seen as a robust RL problem with sigma equal to 0. So I make this line to be dashed. Then we can compare it to the robust RL solutions. So despite significant recent progress, the data cost required to solve robust RL remains an open question, regardless of the divergence function. So we will first focus on a specific one, total variation. The definition is here. Then the prior state-of-the-art data cost upper bound for robust RL is shown in the solid purple line. So this upper bound indicates the sufficient data cost, which means as long as our data size is larger than the purple line, there exists an algorithm that can solve all robust RL problems, making the shaded purple line to be feasible. And because of the state and action assumed to be finite here, but they can be extremely large. For example, in humanoid robotics, the dimension of the state and action will go exponentially as the dimension of the states increases. So this shows that because purple line is higher than the blue line, it kind of tells us, okay, it seems solving robust RL need more data than standard RL. But actually, but this is not sure, because we can find better algorithm to push the purple line down even below the blue line. And on the other hand, the solid red line shows the prior state of the lower bound, demonstrating the necessary data cost to solve all robust RL problems, making the shaded red region infeasible. So because the red line is actually below the blue line, it suggests that, okay, maybe a robust RL need less data than standard RL. So far there's some mystery because of the significant gap between the upper bound in purple and the red line in and the lower bound in red, showing very opposite message of how many data does robust RL really need. So to solve this, we tighten both the upper bound and lower bound, and finally reach the green line. So the green line shows exactly how many data costs will robust RL need, both sufficient and necessary. So that means the green line can move up or down. And more interesting is that we can find the green line is never higher than the blue line, which means that solving robust RL won't require more data than standard RL. And in many cases, it even needs less data to solve.
So Matt has a question. Yeah, Matt, go ahead.
Just to understand, the robust is relative to V star for robust, right? It's the optimum policy over, and that's distinct from V star for the non-robust case. Okay,
Yeah.
and for the robust V star, does the environment change at every time step within the disk of uncertainty, or is just each foray or each episode is perturbed?
Yeah, that's a very good question. So I need to emphasize that actually standard RL and robust RL are two different optimization problems. So their optimal point, which is V star or V star sigma, can be very different. Yeah, and for how the environment, and for the second question, whether the environment is changing every step or it is still fixed during an episode, we don't put assumption on it. It can be anything because we are targeting a worst case. So as long as that environment P is is still in the uncertainty set, it can change every step, or it can also be still fixed within each episode. But as long as it's inside the uncertainty set and don't be outside, this V star sigma won't change. So actually, it depends on whether the uncertainty set change or not. The uncertainty set will be fixed and prescribed before we define the problem. Yeah.
Okay, so if that's the case, the uncertainty set, the volume of the uncertainty set presumably grows exponentially with some dimension of the observation vector, right?
Exactly. Yes.
So, and you're saying you don't need to increase the number of samples to learn how to contend with this?
Yeah, I think yeah, I hope I understand your question well. So actually people make some assumption on the uncertainty set. I didn't get into detail here, but yeah, people will put the uncertainty set is over the entire state and action space. So here we are considering a class of uncertainty sets called SA rectangularity. Satisfies an SA rectangularity condition, which means the entire uncertainty set can be decoupled into many small uncertainty sets over each state and action. So that means when we visit some state and then we decide for the action, the uncertainty set is explicitly defined for that state and action, and all the state actions own uncertainty sets will finally form the entire uncertainty set. So it's make this distribution robust RL problem well posed.
I see. Okay. For a trivial example, it does not encompass the possibility that the handle jumps around in some volume on every time step. Okay.
Yes, exactly. Yeah, that's a very sharp observation. Yes.
Okay.
So people usually just put some rectangularity to make the problem to be feasible at least, or it will be like a bit hard to solve. Yeah.
Okay. Thanks.
PAD, something like that. Yeah. Thank you so much for the very insightful questions. Yeah. Okay. Yeah. So yeah, I ignore I didn't mention some details, but yeah. But if you're interested in the details, welcome to see your paper, The Curious Price of, yeah, this one is, yeah, it just it's just get a minor revision in operation research 2 days ago. So yeah. um okay, so then I will continue. We can have all the questions along the talk or after the talk. That's all great. Yeah. So okay, so the results for the total variation is that we can see, because the green line represents the data cost required for robust RL in a kind of rectangular conditions way, and the blue line represent the data cost for a standard RL problem. So it kind of shows that robust RL require no additional data cost than standard RL. That's very exciting because it encourages practitioners to adopt such kind of robust RL formulations. They can achieve additional robustness against standard RL without needing additional training data set. Okay, but we may wonder, can we always have such robustness without requiring now more data phenomena, or it's just a coincidence for the total variation under this set? So to explore this, we study other types of divergence function. Next, we will see a class of divergence function based on LP norm for any p bigger than 2, measuring the LP norm of the difference. So we will see some very familiar, very similar phenomena here. So solving robust RL still don't need more training data set than standard RL, and even less in a lot of cases. Then we turn into the uncertainty set using chi-square divergence, which is widely used in statistics, belonging to F divergence family. We improve both the upper bound and lower bound and reach finally the green and yellow one. While they still don't match with each other, leading a very interesting future direction, but the message is already very clear that because of both the upper bound and lower bound never lower than the blue line, showing that actually solving robust RL, if we use chi-square divergence to define our uncertainty set, then solving robust RL can be much harder than standard RL, which means that we may need a lot more training data. So the takeaway is that if we're summing up all the results we have introduced, is that actually whether robust RL need more data or less data to solve than standard RL is not a very it's a task, or let's say uncertainty set dependent answer. If we use total variation or LP norm, solving robust RL need less data than standard RL. But we also need to be very mindful. For example, for the chi-square divergence, solving robust RL will need much more data than standard RL. So this motivates both theorists and the practitioners to use maybe robust RL formulation, but at the same time need to be very mindful how to choose the uncertainty set so that its statistical property won't be too bad. Okay, that's there's some technical insights that's why using different uncertainty set will lead to very different results. But as the time is limited, I will first skip them. If you're interested, welcome to ask that during the Q&A session. So going beyond the theory we have introduced, it's equally important to enhance real-world reliability in practice. So we introduce some benchmark for robust RL called robust gymnism. So a unified RL, robust RL benchmark for robotics and control. So that's people can create diverse robust RL tasks based on over 60 task bases from standard RL, safe RL, or multi-agent RL. And for robotics control, we also implement proposed algorithm based on what we have introduced, so that adds some penalty term to the cost function in safe RL to avoid the some safety issues when robotics trying to work. And besides that, there's also a lot of application for robust RL on autonomous driving to handle the relationship between the brightness and traffic density, and also in many resource allocation problems like 5G wireless network. When the customer demand is changing over time, how can we have a robust algorithm to satisfy the the users' demand, but also minimize the cost of our power. Yeah. So there's a lot of future opportunities for robust RL, both in foundation methodology side or application side. For foundation sides, we already seen like different uncertainty sets can lead to very different things. And also when it's extended to multi-agent system, what will happen? And application is also very, RL now have a lot of things that can be used, like in post-training to robust to less data noise, or let's say the reward is not always the correct one. Also for robotics and agentic AI, something like that. So there's plenty of opportunities to apply and also develop new algorithm for it. Okay, that's the first part. Yeah. The second part about multi-agent systems is actually very short. And so if we give a very brief summary of the first part, that's we try to see whether data efficiency and robustness can be simultaneously satisfied without hurting each other. And at least from the theoretical side, like we can see that there's some possibility. And the second part, we will see like whether we can make the computation efficiency and robustness to exist together, but don't hurt each other and even help. So this part is about more about strategic games, because there are so many strategic multi-agent systems exist in the world where agents interact and influence each other in our modern life. So examples include robotics and manufacturing, autonomous driving, and also in agentic AI, inside the agents, there actually usually is the multi-agent systems that so many LLM or foundation model are collaborated with each other and also interact with the human to accomplish a task, in a collaborative way. So many of the systems involve both AI and humans, adding complexity to their interactions. So these strategic multi-agent systems can be naturally modeled as games, where each agent aims to maximize their own outcome, but its outcome also depends on other people or other agents' decisions. So within these games, can we find the optimal solution in the views of any involved agent? So those concept usually called the equilibrium, which represents a stable point of agents joint strategies where all agents will be satisfied with their current strategy and don't want to move, giving all other agents are also fixed. So one of the this equilibriums is well known is called the Nash equilibrium, which assumes agents are risk neutral and rational. So here risk neutrality means agents are not aware of risk. They treating outcomes of all decisions or cases equally without distinguishing between safe and risky cases. And rationality implies that agents are perfect optimizers who make no errors. So if with the solution concept like Nash equilibrium in mind, can we effectively learn such equilibrium so that we can provide to the agents to let them behave like that in practice? But actually, one notorious challenge in games is the computation tractability of computing those equilibrium. So computing Nash is generally intractable, can be very hard to finish in manageable times. Besides, except for some highly structured games, for example, two-player zero-sum games. So even two-player general-sum games can be intractable to compute. So ideally, we hope that those equilibriums can be computed in tractable time so that we can really obtain them and use in practice. And actually, another equally important question is about Nash is that what defines a reasonable equilibrium? Is the Nash equilibrium assumption of risk neutrality and rationality realistic and can be predictable of real human decision-making behaviors? So inspired from behavior economics, we observe that Nash equilibriums is not only a computation intractable, but also not reasonable model for realistic human decision-making sometimes. To be more specific, for the risk neutrality assumption, actually a classical finding in behavior economics is that people usually risk averse in the face of future uncertainty of both the environment and other agents' decisions. So such kind of risk aversion reflects a form of robust tendency, which means that humans usually prioritize safer decisions. Risk aversion can be modeled using some convex risk measures so that it will be identical to a robust form in a regularized worst case form, shown by some dual representation theorems. So that shows that actually, as a human, it's not usually risk neutral. We're usually kind of risk averse. And another observation in behavior economics that is called bounded rationality, which means people can be imperfect optimizers and often settle down for good enough decisions, but not perfect decisions due to the time limit or resources limit or cognitive capacity. So these two insights motivates us to model equilibria that considers realistic agents, those who are both risk averse and bounded rational, when modeling their goals and the strategic interaction in game structure. So that's the second goal. Like we usually want some equilibrium that can really be predictable of realistic human decision making. So combine these two goals. One is that we aim to model equilibria that consider realistic human behaviors. And another one is we also want such equilibrium to be computation tractable. are those two goals conflicting with each other? Because incorporating additional risk, because if we want to capture realistic human behavior, we need to incorporate additional risk-averse and bounded rational assumptions into games. It will generally add complexity to agents' objectives and game structure. So will that make the equilibrium of games harder to compute? So in this part, I will share some insights that if we incorporate those realistic human behaviors, the risk-averse, which is a robustness one, and the bounded rational, it can actually help in computation tractability, but not hurt it. To be more, to get into more details, let's first specify how to incorporate those realistic features of human into the modeling of the game. So we start from the original game of n players. Here n is some positive integer. So in those games, each agent is trying to optimize their own utility function, which is the return output function of themselves over the all strategy space that each agent can cover. Here's how we incorporate realistic human features. So risk aversion will be modeled by adding a nonlinear risk function outside of the original utility function, where bounded rationality will be reflected by transfer the space of all strategies into a smaller and smoother class that involves more randomness. People usually call it like some quantum responses class. So this quantum responses is just a subset of all strategies. Now we can ask this question. So will computing an equilibrium for the second game with risk averse and bounded rationality require more compute? So to answer this question, we first recall that computing Nash equilibrium for the original games can be intractable. And also, if we only add risk-averse or bounded rationality, the tractability can be improved in certain games, but it depends on original game structures and can hold for all. But if we consider the game that we just introduced, we call the natural equilibrium for this new game as the risk-averse quantum response equilibrium, RQE. This equilibrium represents a stable point where all realistic agents can be satisfied with their output and don't want to move anymore. Here is the informal theorem demonstrates that for all finite games, including the extension to finite horizon Markov games, which is sequential games, computing this new equilibrium RQE will become tractable as long as the risk function and quantum response satisfy certain conditions. Technically, So, because of the help of this additional risk aversion and bounded rationality features incorporated into the game structure, it makes the natural equilibrium becomes computational tractable. Shows that if we incorporate some robustness tendency, which is reflected by the risk aversion thing, it actually will help with computation efficiency. Technically, why this tractability happens is because this additional risk aversion and quantum responses can help us to obtain some great good game structure like convex concave games, or let's say approximate zero-sum games, so that computation compute the natural equilibrium for those games with good structure will be possible. Okay, so finally, it's just a illustration for we plot like 13 games of with real human play data to show that the blue region is where the RQE is tractable to compute, and human really will play in these regions. Yeah. Okay, that's all for this talk. Basically, it's just one takeaway message is that incorporating robustness is not just a desired feature for decision-making problem, but also can be some opportunities so that we can not hurting learning efficiency, but maybe can also help learning efficiency. So robustness and learning efficiency are not really two fully conflicting goals. Sometimes they can have good synthesis. Yeah, that's basically the takeaway for this talk. And for long-term interests, I just want to share a little bit for my research interests, so that if any of you are also interested, I'm very happy to talk more and have wonderful collaborations. So my long-term goal is to develop reliable AI to improve human conditions, to leverage the rapidly growing data along with advanced technologies to extract meaningful information. So, besides the two topics that I talked today, like learning efficiency and robustness, is definitely two principles that I really want to design algorithm to achieve. And also, in the short term, very interested in like multi-LM agent systems, how they can collaborate with each other to achieve the real agentic AI, to save time for people and also create some happiness time for them. And also about how we can use decision-making AI to better understand and help people in the intersection between AI and cognitive science, neuroscience, and behavior economics, some social science things. Yeah, that's all for the talk. Thank you so much for listening. And yeah, if you have any questions, please feel free to ask or reach out offline. Yeah.